Okay, so we'll get started here. Like I said, I just want to kind of finish up the chapter we're currently in, because for sure this is going to be on the finals type stuff, so I don't want to kind of cram it in on Tuesday right before the final. And we just have one little section left to go, so we'll finish it up. And then afterwards, we'll take a look at the lab that was for today, which is kind of like a worksheet / you're supposed to build some models. And we'll go through it, and I'll tell you what I'm going to expect you to do from that. And then that will be due probably towards the end of next week. So, but at least you can kind of get a jump on it and all that kind of stuff. Okay, so we've been obviously talking about in this chapter here complex ions. We talked about coordination compounds last time. We talked about how to name them pretty much, how to draw their formulas, how to assign oxidation states, coordination numbers, and all that. So the last thing we're going to sort of talk about is sort of how the electrons get distributed in the sort of transition metal or the metal within the complex ion, and the effect of certain ligands being present as to how they actually do sort of get distributed. So it's sort of complex ions can be different sort of geometries. Hybrid orbitals are formed to share electrons. You remember hopefully hybrid orbitals, right? Like sp, sp2, right? sp3, sp, I was going to say 4, that's it wrong, sp3d, sp3d2. These are related to electron pair geometry, if you remember. So basically, number of electron pairs for each of those is 2, 3, 4. Then your expanded octets, 5 and 6 electron pairs. And those coordinate to a linear geometry for 2, right? For 3 is your trigonal planar. 4 is your tetrahedral. 5 there is your trigonal bipyramidal. And 6 is obviously octahedral here. So we do get some of these geometries that do occur here in sort of complex ions. A lot of times, depending on the coordination number, we'll get really kind of the tetrahedral. We'll also get some square planar that will occur. Linear and then octahedral is a very common one. Now, although Vesper models don't really work well for complex ions, as we've been talking about, ligands are sort of considered like Lewis bases. So we look more of it as sort of a Lewis acid-base interaction that's happening with the complex ion and those ligands that are there. So here is sp3d6, which would be the octahedral arrangement. And typically, octahedral arrangement goes with a coordination number of 6. So just like 6 electron pairs is octahedral, it's the same sort of idea here. So if you have 6 ligands sort of directly attached, in this case, obviously, these are all monodentate, which means they will bind once, which gives us that coordination number 6, and that octahedral arrangement in 3-dimensional space. Some other very common ones are our tetrahedral and our square planar, which is, you know, kind of often an expanded octet. These guys typically are your coordination 4 type of geometries that occur. I think we saw some of that with the isomers we looked at the other day, sort of the square planar geometry, which obviously it's all within the square, right, on the same plane. This guy here, coordination number 2, is again kind of like the linear arrangement, which is typically what we see with somebody with a coordination number 2. As we talked about last time as well, you know, guys with kind of a smaller positive charge will probably hit the more of a coordination 2. Guys with like a plus 2-ish is like your 2 and your 4 and 6. And really the larger guys will get positive charge, will get up to that coordination number of 6. So again, here's sort of our pictures of each of these sort of geometries, which are very common in complex ions and coordination compounds. So let's talk a little bit about the electrons within the metal. And what we're talking about here is the metal in the complex ion and the d electrons, right? So these are our d electrons, and really our d orbitals, I guess is a better way of putting that. As you know, right, there are 5 different d orbitals Each one could hold, right, a maximum of 2 electrons. That's for electron configuration, how we get to the magic number of 10 when we fill that subshell up by putting it in there. Now, in the absence of any ligand being present, that metal's d orbitals are all going to be equal in terms of energy. So they will all be exactly the same energy. But some interesting sort of things happen with those d orbitals when there are some ligands that are present. Depending on the type of ligand that is present, it could cause really a splitting of those 5 d orbitals. And this is what is referred to as crystal field splitting. And that is the energy difference between the obviously 5 different orbitals. And what we're looking at here is a coordination number of 6 and an octahedral sort of splitting that we are looking at here. And what ends up happening is, depending on the ligand, when those ligands get there, we get the kind of XY, YZ, and XZ there, and all of our squared guys go up higher in energy. Now, what this affects is how the electrons will sort of populate the d orbitals in the presence of ligands. Now, in a normal d orbitals here without any ligand present, these are our d's. We would fill these guys like Hund's rule there, right? One at a time, right? And then come back and start filling them up, coming back through. Now, when we get the split in these orbitals, what's going to happen is the electrons are going to fill like normal, which means electrons always fill lowest energy first, right? And then go to higher energy as they fill their electrons. So let's just say we have like 4 d electrons that need to be sort of populated, if you will. Now, what's going to happen is they're going to obviously start here on the lower end of energy and populate these orbitals, you know, like we normally would expect. But now when it comes to sort of our 4th electron that we want to populate, the distance here, or the amount of energy difference between the lower d orbitals and the higher d orbitals, makes a difference as to where that 4th electron goes. If this is really large, that electron is going to go, I ain't going up there. I'm going to go this way first and populate at the lower energy level. And it will continue to populate the lower energy level until basically it runs out of options and needs to go up there if possible. Now, in certain situations, if we have a much smaller difference there between the upper and the lower d orbitals, so this now is more smaller distance, then the electron will go up kind of like normal and sort of fill it one at a time. The next electron would come over here, and then it would come back through and really kind of pair everybody up like a normal sort of distribution. So the crystal field splitting is that energy difference between sort of the lower energy d orbitals and the higher energy d orbitals in the presence of a ligand there, causing that splitting to occur. That is sometimes abbreviated with the little delta symbol. It's also E as well, which is energy, which is that splitting there. And we could calculate that crystal field splitting by using an equation you probably remember, which is E is equal to H times the frequency, H being our friend Planck's constant, which is 6.63 times 10 to the minus 34 joules seconds, or chapter 2, I think, in 200A, or chapter 1, actually, I think, in 200A. That's obviously the frequency, right? Frequency is typically in reciprocal seconds, right? Which is also a hertz, right? And both of those equations really come from C is equal to the wavelength times the frequency, where C is the speed of light, which is 3 times 10 to the 8 meters per second. That is obviously our wavelength in meters, and that is our frequency in 1/seconds there as well. This means, like you might remember this equation, that if you simply just have the wavelength, you could calculate the energy by substituting those guys into each other, that E is equal to hc divided by the wavelength, because the frequency is equal to c divided by the wavelength. So you can substitute that in for the frequency. This means if you simply know the wavelength of light that is coming off or has been entered into that atom, you can figure out the splitting of the higher d orbitals and the lower d orbitals in this sort of octahedral arrangement. Any questions on that? Obviously, we've done some of this this semester, right? We always want to go with the maximum absorption, right? And that's so that all of our values, right, get readings. If we choose way over here as our maximum wavelength, we are not going to get a lot of readings happening here. The other important thing that we talked about and we did, right, is the color of, say, the solution that we see is the complementary color to the wavelength that is being absorbed, right? So even though the solution is red, we don't set the machine to the wavelength of red, right? We set it to the complementary color because that is the color that is being absorbed. Any questions on that there? So here's a problem, but I think you have worked out. So let's just go through kind of the solution there to make sure. The absorption maximum of this complex ion, which is a coordination number 6, is 470 nanometers. What is the color of the complex and what is the crystal field splitting in kilojoules per mole? So we'll start with the color of it. It absorbs light into the 470 region, which is here. I guess blue on blue is not the best choice there. So obviously the complementary color would be across the way on our color wheel, and it would obviously appear orange to us here. That's why I think we were doing red once in our class. And you probably set your wavelength in that 490-ish, 500 nanometer range, again, because that is what was being absorbed. Since we actually only have the wavelength given to us here, we could use the equation that I just wrote there. And once again, sometimes people will just use the little kind of delta symbol to represent the crystal field splitting. Both of these guys are constants, which makes it really convenient. One thing we do have to watch out for is units. Obviously, this is in nanometers, so that is what the times 10 to the minus 9 is there for, to convert it to meters so that all of the units properly cancel out, and that leaves us with joules. That is technically joules per atom, and that is why when we wanted per mole, we see our good friend here, Avogadro's number, right? Which is atoms per mole. That way the atoms cancel out. So the last part of the calculation we ended up with joules per atom using Avogadro's number and multiplying it by Avogadro's number. Atoms per mole. The atoms cancel, leaves us joules per mole, which then you could convert obviously by dividing by 1,000 and get kilojoules per mole. So that is why we're using Avogadro's number there. Question on that calculation there. Okay, so let's talk about what basically determines how the electrons are going to be distributed, what determines sort of the difference in those d orbitals, and it actually is the ligands that are attached. So it depends on what type of ligand gets attached to it as to what type of splitting you might get. And there is what is known as the spectrochemical series, where we have some ligands which are considered weak filled. And what weak filled basically means is you're going to get a small separation between the lower d orbitals in the octahedral arrangement and the higher d orbitals. So I'll just draw them like that. And what that's going to do is, for example, again, if we had, say, 6 d orbitals we wanted to sort of fill in there, because our guy here is weak filled, we will fill these electrons like normal. We would go 3, then it would go, it's not that high up there, so we'll just fill those one at a time, and then we would come back here. The result of this is we get a lot of paired or unpaired electrons here. Unpaired electrons, right? Paramagnetic, yeah. This is what is sometimes referred to as being a high spin complex. High spin complex because it has a lot of unpaired electrons. And that's different than if you hit some ligands which are considered strong fields. So strong field means that those separation for dramatic drawing purposes will look something like this. Is very large difference between those two. And let's say we wanted to distribute the same 6 electrons. What's going to happen when you distribute these electrons is going to go 1, 2, 3 and go, no thank you, I don't want to go up there. And it's going to come back on the bottom here and actually start pairing them off. And in this particular case, we have how many unpaired electrons? None. They're all paired up. And this is what is considered a low spin complex. And it's a very common question with this crystal field splitting is, how many unpaired electrons do you end up with? It's a very common sort of question. And it is the ligands that determine that. So here's sort of the split. You know, we have these guys on this side, which would be strong field. We have these guys on that side, which would be weak field. We have some guys in the middle, which can kind of go either way, to be honest with you. So in certain problems, they'll say, hey, do it for strong field or do it for weak field. Or they'll say, do it for the high spin complex or do it for the low spin complex. If you do it for low spin complex, you should have a larger separation, more paired electrons. If you do it for the high spin, you should have more unpaired electrons that occur. In certain cases, you may not be given any directions. And the reason for that is it will not make a difference because maybe you only got 3 electrons to distribute, which means nobody's getting off the ground floor there no matter what you do. So, you know, in some cases it won't make a difference. In some cases you could do high spin and low spin and you'll end up with the same number of unpaired electrons. So again, in certain cases, it really won't make a difference. So if you come across a problem or something like that where you know, maybe they don't give you direction, maybe it's somebody kind of in the middle-ish, you know, it may not make a difference no matter which way you do it, it might come out the same. Any questions on that there? So once again, what we're currently looking at is specifically the octahedral splitting, where we kind of have our squared guys going up on top and our kind of non-squared guys going on the bottom here. So let's take a look at what we could do with these guys. So first off, let's take a look at this first one here. And this is our complex ion. And first off, the coordination number here would be 6, right? Br is monodentate. That tells you it's going to be octahedral. And it also tells you that you're going to see that 3-2 split that we've been looking at, again, with kind of our squared guys up on top and our individual guys on the bottom. So what we want to really think about is, you know, BR, what kind of splitting are we going to get there? Make it more official here, x squared, y squared, z squared, and x, y, z. All right, so if we look at this guy, we definitely see Br over here at weak field, so that helps us identify that it is weak field. So we know that our ligand is weak field, which means we're not going to get a tremendously big separation that's going to occur. We also do want to figure out what is the charge on our nickel. So obviously Br is -1, there are 6 of them, which is -6. And we have a -2 left over. That means the nickel here is rolling with a +4 oxidation state. If we look at nickel with no charge, that is lucky number 28 on the periodic table, which is argon 4s2 3d8. Nickel with a +4 charge would have only 24 electrons, right? It lost 4 electrons. We talked about it earlier on this chapter when transition metals lose electrons. Which ones go first? they actually will lose the S's first. So when it goes to lose the 4 electrons, it's going to lose those 2. But now it still has 2 more it needs to take out, right? And it's going to come from here. So this guy is going to end up being argon 3d6. Now, what we're talking about here is actually distributing these 6 electrons into our sort of orbitals. So once again, if we redraw it, this is a weak field, which means this is not going to be very large. It's going to be a small separation. So as these electrons basically go in here, they are going to go 1, 2, 3, and go. That's not too high up there. So 4, 5, and one more back down here to 6. We actually end up with 4 unpaired electrons in this case, right? And this would obviously be a high spin complex because we have a good number of unpaired electrons. Any questions on that distribution? Now, why don't you do this one and see what you come up with? So same nickel basically, but we have En as our ligand. So we'll take a peek back there. We'll do En as strong field for this one. So why don't you do it as strong field? Number on this guy would be 6. So that's ethyl diamine. That's one of those bidentate ones. So you get 2 connections per. So this is going to be coordination number 6, which means once again we are going to get the same splitting that we saw before. The En, as we just talked about, we will do a strong field, which means we will once again have our 3 guys on the bottom. We will have our couple guys up on top there. And it's going to be strong field here. When we look at the charge on nickel, it is still +4 in this case because En is neutral. So we are still talking about pretty much the same 6 electrons here. The difference, though, is how these electrons are going to be distributed because we are now facing a strong field is we're going to go 1, we're going to go 2, we're going to go 3, and it's going to go, that is too high up there, so we're going to pair up low first. And in this case, we actually end up with 0 unpaired electrons. And this definitely would be a low spin complex, right? As we have no unpaired electrons that occur here. So again, the difference between the ligands that are present can cause those orbitals to be either greatly spread out or maybe not as badly spread out, is going to cause differences in how those electrons get distributed. Any questions on that one there? I think I'll be happy if you did 3 and 2. Yeah, that'd be good. Other questions on that? Okay, so let's take a look just real quick at the FeF6 one there. So we have FeF6, and it was, I believe, 3 minus. And in this case, we got a coordination number one more time of 6, which is going to give us our octahedral. This is -1, and there's 6 of them, which means in this case, our iron is +3. Iron with no charge is argon 4s2 3d6. Iron here with a +3 charge, which means it's going to kill these 2 electrons right there. It's going to also then take one of those electrons out from the D, and that means that we will end up with argon 3d5. So in terms of what we need to distribute here is these 5d orbitals, our electrons. we would go back to maybe our chart here, and we see F is sort of in the middle-ish. So we will do it for weak filled here. Why not? So if we did it for weak filled, it will look like this. And once again, we would go 1, 2, 3, and it would go, you know what, that's not too bad. 4 and 5, and this would definitely give us a high spin complex. Now, this is one where it could tell you to do it the other way because it's kind of in the middle there. And if you were told perhaps to do it for a low spin or strong field, you know, you would sort of end up like this if this was strong field. 1, 2, 3, and then it would come back this way where we do get 1 unpaired electron only in this case versus 5 in the other case. And this would definitely be our low spin sort of way. So again, sometimes they will give you that direction as to do it one way or the other. And again, if it's some type of high spin, you should have a little bit more unpaired electrons, and obviously low spin, you would have less. Question on that there. So here's the other one that was on that page, which is the CN, and the CN is strong filled, and as you can see, we do get our paired up with our 5 electrons. Again, because in this situation here, the iron is still +3 as well, so it has those 5 electrons that would be necessary. So in terms of octahedral, this next one is sort of all your arrangement. On the left is high spin for 4, 5, 6, and so forth electrons. You can see a lot more unpaired electrons happening over here. And on this side, this would be the low spin, where you have a lot more paired electrons happening. And again, the more sort of unpaired electrons you have can affect sort of some properties, obviously, of the complex ion that occurs. So once again, what we're looking at here is all octahedral coordination number 6 that's happening. You can also do this for other sort of geometries for complex ion. This is tetrahedral, which would be coordination number 4, and it pretty much works the same way. It's just opposite of octahedral. So we have all of our squared guys on the lower energy and our kind of individual guys on the higher. So once again, if it was strong field, they would fill up the bottom first, and then obviously be forced to go up there if necessary. And if it was weak filled, they would fill just like the other guy would do, but kind of do it in his normal way. We would go this way, this way, this way, and this way, and then come back and pair up. So tetrahedral, almost like the opposite splitting that you see obviously in octahedral, and works very similar. There's also a little crazier one that is for square planar, which is also coordination number of 4. Works really the same way. Again, it would fill lowest to highest, so obviously lowest first to the next lowest and the next lowest, and so forth. For us, you are not responsible for the crazy looking one. You're responsible for tetrahedral and octahedral. Yeah? So you're responsible for those two, which are basically opposites of each other, so it shouldn't be too bad. Any questions on that?